Well, good morning, good evening, good afternoon, wherever you are in the world. Welcome to our third series of oil and gas related webinars from Endress Hauser. Today we will discuss water preparation in oil and gas, and the speaker, you can see him next to me on the camera as well, is Ralf Bünder. Ralf works in our factory where we produce instrumentation for liquid analysis in Gerlingen in Germany, and he's part of the strategic industry group for oil and gas within the Endress Hauser organization. But he will introduce himself a little bit later as well, no problem. This webinar will last roughly about 45 minutes, 30 minutes of presentation and 50 minutes of question and answer. But it's very common in the oil and gas industry that before we start to have a safety moment. And today I like to have the safety moment focused on the COVID-19 situation. So please wash your hands on a regular basis. Keep at least 6 foot or 1.5 meters distance from each other. Wear a mask in public. Get vaccinated when you get the opportunity. And make sure that you stay good mental health as well. That is very important. My name is Rob Vermeulen, and I'm globally responsible for the development of the oil and gas industry within Endress Hauser. And I reside on our production facility campus in Greenwood, Indiana, America. But before we start, I'd like to give you a small introduction of Endress Hauser. Here you see our headquarters in the picture on the top red corner. That's in Rheinach in Switzerland. Endress Hauser is a global company, like I said. We have a turnover of 2.6 billion euros, and we employ roughly about 14,000 people worldwide. These are our own people. We also have a lot of representatives. We're financially very healthy. And we're very innovative. We own more than 8,000 patents just focused on instrumentation alone. And with this, I'd like to hand over to Ralf. I see you just took your last sip of tea, Ralf.
Yes, yeah, Rob, thanks a lot.
Go ahead.
All right, thank you. Thank you for the introduction. I quickly introduce myself, and after that I will switch off the camera so that we do not encounter any technical problems here during the presentation. Yeah, I'm 47 years old. Since I'm German, yeah, I'm since 2007 with Endress Hauser. I'm working in the area management department, so that means I take care for some countries like India and the Middle East region. I'm located in the south part of Germany, where we have our factory for liquid analyzers. And another role is that from a liquid analytical perspective, I take care also for the chemical and oil and gas industry. Rob mentioned that. I'm also a member of the strategical industry group. And when there's some time, I like to play soccer. I like fishing very much. And that's enough about me. So I will switch off the camera now, and then we are good to go with that. We continue or go start with the presentation. So just give me a second. Yeah, now it works. And I'm just looking for the laser pointer. Perfect. Yeah, so the content of the presentation, I just introduced it to you guys. That is, we will have a look to the various sources of makeup water, where this water is used in the refining process or in the oil and gas process in general. We will have a look to the various treatment processes. We will talk about the parameter to control these processes, and I also give you some examples at the end of some applications, and hopefully there's also some time left that we can have a discussion, some questions and answers. And okay, let's get started. Before I start with the to go into the applications, I just want to give you an overview about the parameters we offer, because that is of importance, because these parameters play an important role later on when we have a look to the different processes. So pH, that is a very important parameter here, and you see a large variety of different pH probes for various applications. We also offer redox potential, some photometers to measure turbidity, for example, also color. Conductivity is another important parameter, for example, to monitor impurities of water, impurities of steam. Dissolved oxygen is also important. For example, the oxygen level in the steam also has to be kept on a very low level to avoid any kind of corrosion. Disinfection is also an important parameter that comes later. Here, turbidity, I mentioned that already. And here you see a full battery of colorimetric analyzers for various parameters. And when we talk again about steams and silica, for example, we can use, for example, here a colorimetric COD analyzer or a TOC analyzer, or also an optical instrument to detect organic load. And all this becomes, I would say, of interest in the next couple of slides. Just a few words about water sources and their impurity itself. So here you see different, I would say, water bodies. So this is a lake, stream, ocean, a pond, here a river. And when we want to use the water for industrial processes, we need also to consider the various pollutants. Yeah, there are parameters like pH, conductivity, totally soft solids, turbidity, color, hardness, and bacteria, and that all gives information about, I would say, the chemical property of the water. We also need to consider organic pollution like biological oxygen demand, total organic carbon. That gives an information about, I would say, organic pollution. Nowadays also, when we think about agriculture, so the fertilizers also go into the water. So nitrate, phosphate, these kind of stuff also needs to be considered. And just to give you an example, that water is not like just water. So you have here a scale for pH, and you see then different water sources. And if I just take clean rain as an example, so we can face a, I would say, pH range from 5 to 6. And you may have heard about acidic rain. So that was a problem in Europe in the past couple of years. So that will be a range of 4.5 to 5.5. And then we have demineralized water or distilled water, that is 7. And then here for seawater or lake water, there are other pHs. So you see, water is not like just water. So, and that needs to be considered in the further process. So how is the water used in the oil and gas industry? Yeah, we use it as portable water for human consumption in the offices and so on. But then, and I think that is more of interest, water is used for industrial processes. It's used for the steam generation in the refining processes, and depending on the site, also for the power generation. And I will bring an example later. It's also used as cooling water, and in many cases, seawater, for example, is used for cooling purposes. And when we think about upstream applications, then it's used as injection water for the well stimulation to increase the pressure inside the well, and to, I would say, to release the oil from the rock formation. Before used water gets discharged back into the environment in any water body, it must be treated in some cases. Nowadays, recycling becomes more and more important, and we need to monitor the quality. Yeah. So a topic which gains more importance is produced water treatment. So produced water is the water that comes along with the oil out of a well. In the past, that was just then sent to a disposal well and was discharged. But now the reuse of this water for cost reasons becomes more and more important. And in that case, the water needs to be treated. Then recycled wastewater for reuse. And I just give you an example in refineries. So the recycled wastewater is used for the desalter, yeah, to clean the incoming oil and to remove the salts from the crude. And in that case here, to save water, yeah, recycled wastewater is good enough. And cooling water, even cooling water does not change really the chemical property while being used. because yeah, it's just cooling water, but still before it gets back charged into the sea, we need to monitor the quality, and depending on the legislation, you also need to disinfect it. All right, now we going here a little bit more into the process. So really a good example is steam, yeah, because steam is used for the fractionation processes here, for the crackers and hydrotreaters, in the reboilers, and depending on the setup, also for power generation. And this steam has to meet, I would say, different criteria. So if you imagine now steam for the well stimulation, yeah, has also meet some criteria, but that is meet very, I would say, very strict criteria, and we have a look to that. And that brings us to the next slide. So if the makeup water does not meet the quality, and the steam, I would say, does not meet the quality, so what can happen? Yeah, the problem is, yeah, you have silica in the water, you have hardness. Steam, if you deal with steam in high pressure, high temperature environment, what can happen is that you have corrosion. If you do not maintain oxygen, for example, on a very low level, that cause corrosion. Same for pH. You have build up here, scaling. So for example, this could be scaling from silica, from hardness, from sodium. Yeah, and that also then that I would say, yeah, that blocks the pipe at the end of the day, and also that lowers the heat, the efficiency of the heat exchangers. And also here you have some pitting. So we need really to make sure that the water meets the quality criteria. And just some facts here. So 0.1 centimeter deposit can lead to overheating and corrosion, and 5 to 12% of excess fuel consumption. Just consider that has really a huge cost impact. Then once this pipe work is gone, yeah, or has to be replaced, that is also, of course, cost, has also some cost impacts. You have unplanned operational expenditure, and so on. So we really need to make sure that we have good quality. And to do that, here we have to keep in mind a few parameters, which helps us to control the quality. One is pH. Yeah. So in the pipe, to protect the pipe work, usually pH is maintained in the slightly alkaline range. So let's say from 7.5 to 9.2 pH. So conductivity should be in a certain range. Also turbidity is important, yeah, for the makeup water treatment. Gives us also a little bit an idea about the organic pollution. Chlorination is very important to protect the equipment. Yeah. Then silica as a deposit has to be removed from the water, as well as sodium, and hydrazine is used for the deaeration here to keep oxygen on a low level, and total iron. So these are some parameters which helps us to control the processes. And here you on this table, you see some of the criteria. So here for boiler feed water, for the steam generation and refineries, when also power generation is, I would say, included, you have here a pH range, conductivity, so silica in the ppb, so parts per billion, so on a very low range. Dissolved oxygen has to be kept on a very low level. As I said, under high pressure, high temperature, oxygen becomes very corrosive. To remove oxygen, hydrazine is used. In the past, also in some countries it's still used. Nowadays there are also other substances to do the deaeration, to remove oxygen from the water. And same here for the other parameters. So here we need to make sure that we stay below this limits. Okay, typical setup, and this is a very nice picture I got from our friends from Middle East. So if my colleague Ganeshan is listening, then thanks a lot, because he provided this picture. So typically So seawater here is available in large amounts, so that is used as process water. So you have the water intake here. Then there is some pretreatment going on, so that is some rough filtration, really to make sure that there's no sand, no bigger particles coming into the process. And then it already starts with the first part here with the desalination. And in desalination, there are different ways how to do that. You can do that in a mechanical way, that you use reverse osmosis with membrane filters, or you can use a thermal method to remove the ions from the water, and that is a multi-stage flush or multi-effect distillation, and we have a closer look to that later on. Then from there, the I would say demineralized water goes to the boiler and to the steam turbo generator, and here are the gas turbines. The water that is used for human consumption gets remineralized. Yeah, so we need to add some fluor and chlorides that the people can drink that again. Here you have the cool seawater, and the seawater then also gets then back charged here in the outflow. Yeah, so it gets charged back into the sea, and we need also to monitor certain parameter here. So what processes do we have here? Seawater intake, yeah. So there is, I would say, the rough filtration. Then you have a pump house, and you measure the first parameters. So turbidity, to give you an idea about the content of algae. Yeah, you don't want to have this bacteria and bugs and algae in your piping system and in the further process. You have a first check for the pH value, temperature, and conductivity, and then it goes to the chlorination. Chlorination is important because we need to protect the Teflon membranes. And here, the first step here, the chlorination takes place to get rid of the algae and the bacteria here. So these are removed here, therefore we use chlorine. Then we have here the third part. That is, again, that is a mechanical treatment. So we add flocculants to achieve a flotation or also a sedimentation. So that means you add different kinds of polymers. So all the particles will stick to the polymer, and depending what you use, it will floatate or it will sedimentate or settle down. And to monitor I would say, the success of this treatment, turbidity is a parameter. Yeah. So what you want to see then, okay, there's no carryover of these particles here. Then, and now we're talking about the dechlorination. So we added chlorine or chlorine dioxide here, but at this point we have to remove the chlorine. So we also add some chemicals here to remove the chlorine, and here we measure the absence of chlorine. So chlorine has to be more or less zero. Yeah? And again, we measure turbidity, and then it goes this way through a fine filtration to the desalination, to the reverse osmosis. As I said, mechanical, and then to the thermal processes, not and or. Yeah, that is a decision whether you use this one or this one, and in also some cases you have a mixture of this. And then it goes to the demineralization plant. Sorry, that's a difficult word. And from there to the power plant or to the refinery just for the steam. But as I showed you in the big picture, so in the big chemical and petrochemical complexes and refining complexes, the power plant is always part of the package. So then it gets used here. And if the water from here is used for human consumption, or it goes to the public, it goes to the remineralization plant. So we add some salts here, fluoride, chloride, to make it usable for human beings, and it goes this way. So now let's have a little bit a deeper look. So where do we use which instruments and which parameter? So we start with inlet monitoring. Here we have three different sources of water. So could be groundwater, surface, so groundwater from a well, for example, surface water from a lake or a river, and seawater. Seawater we discussed already. So for ground or well water abstraction here, you want to measure level, because you want to measure the water level here. Then the water is pumped this way So you need to measure flow to know about the amount of water and the volume, what you pump here, pressure. And then here you have already the first quality parameters. And you measure turbidity, nitrate, yeah, because we are talking about groundwater or well water, so nitrate can be there, conductivity, and also TOC to give an idea about organic pollution. And from there it goes to the water treatment plant or to make up water. Surface water, it's more or less the same. Yeah, you take the water from a lake, for example. Again, you measure level, you have flow, pressure, temperature, and then the quality parameters, pH, turbidity, conductivity, and so on, and seawater abstraction that was discussed. And from there, it goes to the further treatment. Then we have the mechanical treatment, some rakes, so that is a rough screening to really to take out bigger particles. And then first step, what we do is a pre-disinfection and pH settling. And if we have a look here to the parameter, so here first it's chlorine bleach. So the disinfection takes place here. So there's level. Then you have the adjustment of pH. In that case, caustic soda is used. Again, level, flow, and from there, here the quality parameters in that case is pH and the chlorine level, because you did see chlorination here first. Then it goes to the second part of the mechanical treatment. You remember that was the coagulation. So that is flocculation and sedimentation. So you add these substances, most of the cases polymers, into the basin. They get mixed here and get in contact with the water. The raw water comes in. Again, you can measure pH here, and then the reaction takes place. So the particles will stick to the polymers and will settle down. And the clear water or the water goes then in that way. Here this is a mixing chamber, I would say. This is the clarifier. So the particles will settle down and they go to the sludge treatment this way. So you have to measure suspended solids here. Flow is measured there as well. And the clear water is going this way to the filter, and turbidity is measured to make sure that there is no carryover of particles here. Yeah. So just to check and to monitor that these both processes worked out fine. And then we go to the demineralization with ion exchanges. In that case, then the pre-treated raw water goes into the first, I would say, contact chamber or a vessel. So you add. So what happens here is that the ion exchanging takes place here in this columns, and from there it goes to the second one. So from there, then you have already desalted water. It goes to the further treatment. Then it's desalted and desilicated water. So also silicate was removed, and from there the water is more or less ready then, and it goes then to the further process. And here at the end, you measure here flow, conductivity, yeah, to make sure that these processes before that they went well, and also pH. Yeah. That was with the ion exchanger. And if we have membrane filtration here, or both, here on this picture you see this big, I would say, membrane filters. So that is usually Teflon membrane. Teflon works very well in regards to the pore size. Yeah, so the filtration works very well, but these membranes are very little bit sensitive. So we need really to maintain a certain quality. Yeah. So the raw water comes from the pretreatment. Then there's a first microfiltration, a nanofiltration, and here again we check some quality parameter. And important is, of course, that there are no particles here, and also that the chlorination takes place, that we do not have any biofouling here, yeah, or if the bugs would grow on the surface here on the membranes, then they could not do their job anymore. Therefore, the chlorination is very important. Then it goes that way, and then we go through the membranes, and then the desalinated water can be used. And here again, we measure the organic content, so nothing should be present here, and also conductivity to make sure that the filter worked very well. If there is a breakthrough, that will be detected, and then you can backflush these filters, or you can do your countermeasures. Well, then just to, I would say, to complete that, we spoke about, if you remember the first picture with this plant in the desert, there are different possibilities to do this kind of desalination. And they are also combined, I would say, designs possible. But here with the multi-stage flush distillation, the seawater comes in, it's heated up, yeah. You have, I would say, the condensation takes place. Then the fresh water goes out. More or less the same, just a different design. But again, here also you need steam to heat up the stuff. You have more or less the same. So you take off the brine and also then the distilled water. That is just another setup. And in difference to that, you have the reverse osmosis, and this is a mechanical process. This is, you can say it's a filtration. Yeah. Here you see some pictures. That you can imagine how this, how the dimensions are and how this looks like. So there are advantages and disadvantages, I would say, in both cases. If you go for the if you go for the thermal process, for the multi-stage flush, I mean, that is a very reliable and robust process. There's a long-term experience, more than 30 years. It's not sensitive to feed water, so it takes any water. It has a long service lifetime. And significant cost savings due to the possible manufacturing in the client country, because that can be done. You do not have to import this filters. The disadvantages are that you have higher specific investment costs, and of course here this is the energy consumption. Yeah, that is of course a concern, and it is limited to high capacities. So you have to feed this unit with water, that everything works. So it cannot run half filled. If I say it in very simple words, in difference to the reverse osmosis. Yeah. So how much water you push through these membranes, that is up to you. Up to the needs, I put it like that. So that is in general, we can say there are lower specific investment costs. There's definitely lower energy consumption, because you do not heat up the water to create steam and vapor, and any capacity is possible. Disadvantages, it's sensitive to the feed water quality. That is the reason why we need to measure all this parameter, and potential risk of biofouling. And as I said, if the membranes are blocked with bacteria, with algae, with some kind of biofilm, they cannot work that properly anymore. So there's a strong dependence on the membrane and module manufacturer. High qualified manpower needed for the operation and maintenance, because you need to control all these processes. And there's a higher consumption of chemicals to do all this pretreatment. Well, and if now the makeup water has the desired quality, we are going then into the steam generation. Yeah, the steam used for the fractionation processes and all the processes on the refinery, and maybe also for the power generation. And here you see, I would say, a bunch of different parameters, starting with pH. So you have the feed water, so you want to have an idea about the incoming feed water. Then you go further to the process, so to the feed water tanks. Then you have a preheater. Here again, you want to detect, or let's say monitor the quality about the boiler feed water, that it meets the criteria before you go into the steam generation. Then you have also the desulfurization. Also here you want to measure pH, And then finally, after cooling tower, after wastewater treatment, if it goes to the wastewater treatment, before the water gets discharged back to a river or to a water body, again, pH is of interest. So pH is, I would say, one of the most important parameters here in this process, or in the processes in general. Conductivity is the second one, to gives you always an idea about all the impurities, salts, all that stuff you don't want to have here in this process. Yeah? So conductivity should be very low. Then oxygen. Here in these cases, oxygen has really to be on a very, very low level. I said that already 2 times. And here in the wastewater treatment, oxygen is also measured, but for different purposes. Then you have other parameters like silica, ammonium, phosphate, and so on, to detect impurities for pH conditioning for different purposes. Then turbidity here. Here again is the feedwater to really also to give the information about the I would say biological content and turbidity in general. And here's the same for the disk for wastewater. Silica here.
Ralf, can I stop you for a second? Because we lost you for a few seconds. Can you repeat the last 10 seconds?
Oh, okay. Yeah, I just said that we have this various parameters here, and then was here. So these are the limit parameters before final discharge, and then you have to, or you can use a sampler, for example, and there's in most of the countries there's a limit for the organic parameters like COD, TOC, nitrate. So you see all, I would say, the different parameters that can be used and have to be used on site. So now, so what is different of this parameter in comparison to these ones? So these ones are here in the steam cycle. So we need some kind of pre-treatment in order to measure them. And this is done with steam water analysis panels, because we want to detect the steam quality. And in that case, we have to bring down the steam back to water. Yeah, so that means we need to depressurize and to cool the water in order that we can measure the various parameters. And here you have different setups. So what you see here and also here, these are the cooling units. So to cool down the sample, so cooling water is needed here, and to depressurize the sample in order that we can measure here various parameters. This design is supposed to be used in Hazardous area that we collaborate here with the company Shell. So we follow their design specifications. So we use and also, I would say, the material what they suggest. I just had this morning a question, just maybe as a side comment. Problems with the cooling unit. There was some buildup of calcium, and then this unit failed, and that was due to the fact that they use stainless steel in that case, and they also did some installation mistakes, I would say. And the recommendation here is to use alloy 625, really to, I would say, to have a good quality cooler that don't fail. Just as a side comment. So that was a reason to collaborate, or one of the reasons to collaborate here with Shell, that we really come up with an industry solution. I would put it like that. Then we have the SWOS compact system, so also very, I would say, system. So you see here a multiple flow assembly, the ion exchanger to measure certain parameters, and this is a very compact, small design, can be used to a certain pressure and temperature range. Here, this is a solution, I would say, for the oil and gas industry. So you need to have a system for hazardous area, and also it's suitable for all pressure and temperature ranges. Good. Then after use, so cooling water network is also very important. Usually also the cooling water gets chlorinated to avoid that you have the growth of algae here on this surface where the water passes through. And I've seen that a couple of times, and you see in very old cooling towers where you have some wooden plates here, and you see really the water passing by, and you see this green layer. Really, you see like looks like plants and leaves and stuff like that. And that is, of course, what you don't want to have, because then really I would say, the efficiency of your cooling tower is definitely impacted by that or affected. In that case, many cases, chlorination is done of the cooling water that you don't have these issues. And once the cooling water is used, it gets discharged back into the connected water body or into the sea. And of course, but because what you want to avoid is a breakthrough of hydrocarbons into your cooling water, and that's then the hydrocarbons also get discharged back to the water body. That is what you want to avoid. And to avoid these leakages or to detect them, usually TOC is a very good parameter. Also oil and water in some cases is measured. And this is, I would say, common practice. And in Middle East, they also measure other parameters. So they measure then the full bench. They really want to see then, is there any turbidity, pH, conductivity, but TOC, oil and water, that is common all over the world, I would say. So disinfection packages are essential at all the cooling towers outlet, yeah, depending on the local legislation, but also at the inlet to avoid biological growth here. Well, then just to give you a little bit an idea how these measuring panels can look like, here I just selected 3 different ones. Here that is a multiple flow assembly. We measure here turbidity, pH, conductivity, ORP. Here in the makeup water, not in the steam cycle, but here in the makeup water. Then this is a chlorine panel with pH compensation, conductivity, and here another panel with turbidity, pH, and conductivity and redox potential. So there are various, I would say, setups of these panels possible. You can buy them ready-made from Endress Hauser, no problem. Just to give you an, I would say, real example from site. So this is the LNG plant in a utility application in the Emirates from ADNOC LNG. And we have the reverse desalination here. Then here at that point, we measure the pH. Then it goes to the cation exchanger. So you measure conductivity at this before the cation exchanger and then after the cation exchanger to make sure that we don't have any impurities left. And then the boiler feed water with good quality gets into the burner. Then here we have then the high pressure stream. It goes to the steam turbo generator, and then it's used for the various purposes. Here again, you measure conductivity, and this is just a second, I would say, a repetition of the first one, a second train. So you see here then the various measuring points, and these are the panels. So this is local make. That is, these are done by a local system integrator we cooperate with, and these are the Endress Hauser instruments here, and then you see here the various panels. So installed in the reverse osmosis desalination and at the cation exchanges. And I would say that is a very, very common installation. So pH, conductivity, that is you find all over the place. All the other parameters I mentioned in the steam cycle, like silica, hardness, and these kind of stuff, you also will find some, but then it depends really then on the local water source. There's another picture. So you see different panels here, also in Middle East. So again, thanks to my colleagues in the Middle East who provided these photos. So thanks a lot for that. If you are listening. And then this is the last example. That is, these are panels are installed at Qatar Petroleum at the utility water connecting point. So that means there is a local utility provider. They provide the water, the makeup water, to this client, Qatar Petroleum, and to measure that the makeup water meets I would say, the criteria and the quality. They have these measuring stations in place here to measure pH, chlorine, and conductivity, so that they are sure, okay, the water comes in a good in a good quality from this provider, and we can use it without any doubts in our process. And therefore, they use these panels. And that was the last slide. So thank you very much for your attention, and then we are open for your questions. And I open up my camera as well, that we can.
I will do the same, Ralf. No problem at all. First of all, thank you very much for a great presentation. I think we saw a lot of detail, and we got a good feel for the processes that are at hand in the water and utilities water preparations for oil and gas plants or chemical plants or many other plants as well, I think. So first of all, I like to point out as well the handout in your handout screen on the right hand and the right hand side of your screen. You can have the handouts for download as well. These are available. And with that, I will go to the questions. Let me have a look at the questions. Yes, this is an interesting one. Do you need transmitter boxes for every parameter?
No, due to the fact that we use digital sensors, we don't need that, except when we talk about the Hazardous, the two-wire platform, Hazardous transmitter, then you have an individual transmitter for each parameter. If we go for non-hazardous applications, then you can use multi-channel transmitter. That would be then, in that case, our liquid line. We can connect up to 8 channels. But for the two-wire platform, you need an individual transmitter for each parameter because of the X certificate.
Okay. Then the next question. How big is this silica issue? We only measure pH and oxygen now.
Yeah, that depends on the water source. So if you have, for example, so the water in general is in contact with the ground, and so there's interaction. So you have the salts dissolved in the water when it's passing the soil. And if you have then I would say if the groundwater, for example, contains a lot of silica, in that case, because the ground itself has all the silica and it gets dissolved in the water, in that case, then it makes sense to measure it. When you have very soft water, yeah, as a water source, then you can maybe avoid measuring silica, because it's then not such a big problem. The silica is a problem when you have a precipitation of sodium or silica, because the problem is really that blocks your pipe or the heat exchangers.
And on the water that you have, apparently. Yeah.
Yeah, and that has some really huge cost impacts. So that everything depends on the quality of the water and the pretreatment.
Okay, then I have a calibration question, Ralf. This is from Sam. We calibrate our pH sensor every 3 weeks or so. Can your transmitter tell us when calibration is needed?
So again, we have to distinguish between two-wire and four-wire. So for the two-wire platform, and that is mainly used in refineries, we also developed for Shell a device type manager that is able to give information about the history of the past calibrations, and having that, then you can make a prediction into the future that you can potentially prolong the calibration interval. So that is possible with the four-wire platform, with the liquid line transmitter. We have currently, I would say, even more possibilities with a system that is called Heartbeat. And this is really, that goes in the direction of predictive maintenance and gives you exactly the status of the sensor. So what is the shape of the sensor? How long can the sensor be used further on? And it also tells you when it has to be calibrated. Yeah.
Is that Heartbeat? Is that the same as MemoSense?
No, MemoSense is the technology of data transmission and the coupling between the sensor and the cable. That is what, and MemoSense is the protocol at the end of the day, because this is new, not a new technology that is already available since 14 years. And that is mainly that we measure an analog signal, like in case of pH, it's millivolt potential. When we measure, for example, dissolved oxygen, it could be nanoampere, and these are analog signals. And from the sensor immediately, they get this analog value is converted into a digital one, so that means 0 and 1, and is transmitted then to the transmitter. And this protocol is what we call MemoSense.
Okay. Then I have a question from Ephraim. On slide 18, membrane filtration system. How do you detect filter failure in that system?
I think that was about the reverse osmosis. So first, they measure the pressure, yeah. Also the pressure, if there are pressure leakages, so that means if the membrane is destroyed, that is one possibility to detect it. And then you also will have carryover. So that means if the filtration system does not work anymore, you will see that, because then you have an increase of turbidity and also conductivity at the outlet of the membranes, because the impurities move through
huh?
and go through, and then you will detect it.
Yeah, makes sense.
Yeah.
Good. We are 1 minute over our time slot, Ralf. So I have to end this webinar. So thank you very much for presenting.
Thanks
Thank you very much for being with us and battling through some of the issues we had with the microphone, because it came in and out sometimes a little bit.
Yeah.
But these things happen, I guess. So with this, thank you very much and have a great day. Ralf, any last words?
Yeah, again, thanks for your time. It was a pleasure. And I really, really hope that we will see us in a couple of months, hopefully on your sites, live vis-a-vis, yeah, like the Frenchman says. Because, I mean, webinars are nice, but it's much nicer to talk to you on a personal level.
Absolutely.
Yeah, thanks a lot.
So next week, same time, same place, new topic, oil and gas related. Please make sure that you put it in the agenda, and we hope to see you then again. So thank you very much. And with this, I end the webinar. Thank you.
Bye-bye.